In this example, I want to use z-scores to answer questions about observations made from different populations. So in this problem, a manufacturer makes bags of popcorn and bags of potato chips. The average weight of a bag of popcorn is supposed to be 3.08 ounces, and that's what they would put on their bag, with an allowable standard deviation of 0.05 ounce. The average weight of a bag of potato chips is supposed to be 5.06 ounces with an allowable deviation, a standard deviation of 0.03 ounces. A factory worker or a quality control inspector randomly selects a bag of popcorn from the assembly line and it has a weight of 3.04 ounces. Then the worker randomly selects a bag of potato chips from the assembly line and it has a weight of 5.04 ounces. So what we want to figure out is which one, the bag of popcorn or the bag of potato chips, is closer to meeting the required target specifications. Now, if we were comparing test scores from two different populations, it would make sense to say that the higher z-score would represent the higher relative score, or if we were talking about something like golf scores, the lower or smaller the z-score would be the relatively better z-score, because in golf a smaller or a lower score is considered better. For a problem like this, what we're looking for is a z-score that is closer to the mean. So I've summarized the information here. For the population of popcorn bags, the average weight, or mu, okay, this would be mu, is 3.02 ounces, and the allowable tolerance or deviation from that mean is set to be 0.01 ounce, and that would be our sigma. For the population of potato chips, the stated average weight is 5.02 ounce, so that would be the mean for this population, and its allowable standard deviation is 0.05 ounce, so that would be sigma. So the popcorn bag that was randomly selected was 3.05 ounce, and the potato chip bag that was randomly selected was 5.06 ounce. If we look at these, they're both above the mean, which is great for the consumer, but they are distributed differently. They have different standard deviations. So in terms of the manufacturer's perspective, we want to see which of these indicates that the manufacturing process is working better. So I'm going to convert both of those to z-scores, both of these observations to z-scores. Now the z-score formula is equal to our x value, that would be a single data point or an observation, minus the mean for that particular population, divide by the standard deviation for that particular population. So for the popcorn bag, oops, not popcorn, popcorn, the z-score would be 3.05. A common mistake is to switch these in the numerator. If you do, you're going to get a z-score that's negative when it's supposed to be positive, and vice versa. So we have our observation, the randomly selected popcorn bag, minus the mean, divide by the standard deviation, or that allowable tolerance. Now notice, because our observation is above the mean, this numerator will be positive, so I expect this z-score to be positive. If you get an observation that is below the mean, then you should expect your z-score to be negative. So inputting into the calculator, if you want to do this all in one step, I strongly suggest using parentheses around the numerator expression. So doing that in my calculator, 3.05 minus 3.02, I could have done that in my head, sorry, divided by 0.01 is a standard deviation of 3, or a z-score of 3. So what this means is that this observation is 3 standard deviations above the mean. And that is actually considered an unusual value. Any z-score that's 2 or more is considered unusual, and any z-score that's -2 or less is also considered unusual. Okay, so now we have the potato chips. Let's find that z-score. The observation was 5.06, that was the randomly selected bag's weight, minus the mean for that population of potato chip bags, and then divide by the standard deviation. Again, I'm using parentheses around my numerator expression. All right, so getting this into my calculator, we get a standard score of 0.8. We can call a standard score a z-score, and you can consider the x value or your observation the raw score. So in terms of the manufacturer's perspective, the assembly line for the potato chip bag is performing a little better because based on the single sample, its z-score is closer to the mean. If these two scores were identical, in other words, if the potato chip bag had a mean, or a weight exactly equal to the mean, then this z-score would be 0. So in terms of which one of these assembly lines is closer to meeting the required target specifications, it would be the potato chip assembly line. This z-score of 3 indicates to me that the bags are being overfilled. Now that might not be a problem for the consumer, but it is for the manufacturer.